In this video, we're going to take a look at a new concept called similarity, and specifically we're going to look at similarity in triangles. So let's jump in and first take a look at the idea of similarity and what that means. So as you can see here, it says that a similarity transformation is where we perform a composition of one or more rigid motions. So remember, the rigid motions would be your translations, your reflections, and your rotations. So we do one or more of those, and then we also do a dilation. Now remember, a dilation is not considered a rigid motion because unlike rigid motions, dilations don't preserve segment lengths. They do preserve angle measures, but they don't preserve segment lengths. Now, what dilations do is they change the length of segments, but they change them by by the scale factor. So basically, if we look at a segment that gets dilated and it gets maybe multiplied by 2, the length of it gets multiplied by 2. Well, if there was other segments in the figure that got dilated, then they would all have their lengths get multiplied by 2. They kind of have that common, what we call the scale factor, right? Where all the lengths are going to get multiplied by the same amount. If it's an enlargement, it gets multiplied by something bigger than 1. If it's a reduction, then they get multiplied by something between 0 and 1, which has the effect of reducing the length of it. So we're performing these rigid motions, and then we're performing a dilation. That's called a similarity transformation. So the idea of similarity just means that there is some kind of similarity transformation that will map one figure onto the other. I think of it a little bit differently, though. Similarity, if you can tell that two figures are similar if two requirements are fulfilled. And so let me list those out here real quick. Similar figures will have all corresponding angles congruent. So all the every angle in the image will have a congruent angle in the pre-image. So all corresponding, oops, I forgot to put the angles in there. Let me just modify what I wrote there. All corresponding angles congruent. And then the second thing that will always be true if two figures are similar will be that all corresponding side lengths or distances will be proportional. And so what does proportional mean? It simply means that whatever we have to multiply one side length by to get its new length, we multiply all the side lengths by that scale factor to get their new lengths. So for instance, if we look over here, we have this triangle XYZ, which is going to be like our pre-image. And so we can see that first that pre-image got dilated. It got enlarged to this segment, and then it got rotated around point C. It looks like it got rotated by maybe 90 degrees around point C, and it turned into the image ABC, triangle ABC. And those two would be similar because we did this similarity transformation. We dilated, and then we performed a rigid motion, which was the rotation. So if I look at that, and I look at this definition of what similarity is, what I know is that angle Y and angle B are congruent. So angle Y would be congruent to angle B. I would know that angle X and angle A are congruent. Angle X is congruent to angle A. And then angle Z and angle C are congruent. Angle Z is congruent to angle C. And so that's that first part of the definition of similarity, that all the corresponding angles are congruent. The second part is maybe a little bit trickier. It says that all the corresponding side lengths are proportional. And so what that means is if I take xy, and let's say xy got multiplied by some scale factor n to turn into AB, then that same scale factor would be used to multiply segment YZ to get the length of segment BZ, and to multiply times the length of segment XZ to get the length of segment AC. So if we can write that a couple ways. We can say that n times xy equals AB, and we can say that n times zy equals CB, and we can say that n times xz would equal AC. But another way we can do this is we can take each of these equations and solve them for n, which would just be In this equation, we would divide both sides by xy. In this equation, we would divide both sides by zy. In this equation, we would divide both sides by xz. And every time we do that, we're isolating the n. We're solving it for n. And so that would take us to like a new statement that we could make about these shapes and their side lengths. It would look like this. Since n would equal ab over xy, it would also equal cb over zy, and it would also equal ac over xz. And so every time we took that new side divided by the original side, right? The image side divided by the pre-image side, image side divided by pre-image side, image side divided by pre-image side, we always end up with this scale factor of n, whether that be 2, if we doubled all the lengths, or maybe it's 1.5. If we made each length like half again as big, we multiplied it by 1.5 to get the new length. In any case, every time we kind of divide the new length by the old length, we end up with that scale factor. So we could look at it this way, or we can look at it this way. Either one of these kind of statements is saying the second part of our definition over here, that all the corresponding side lengths will be proportional. And of course, this is because all the corresponding angles are congruent. Now, the last thing we see on this slide is that all circles are similar to each other. We probably won't use that too much, but it just usually is kind of stated along with the idea of similarity. Since circles don't really have side lengths and they don't have angles, we just look at circles and we say, well, every circle is similar to every other circle. But if we're talking about triangles or other kinds of polygons, we kind of rely on this definition for whether or not they are similar. So on that previous slide, we looked at the definition of similarity that applies to all polygons. It applies to triangles and triangles and quadrilaterals and pentagons and any other kind of polygon you could have. If it satisfied that definition that we looked at on the last slide, then we could say those two polygons would be similar to each other. Triangles, however, have a few shortcuts that we can take. And that's what we're going to look at over the next couple of slides. We're going to look at some of the shortcuts that we can use to try and say whether or not two triangles are similar. And the first one says that if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. And we call that angle-angle similarity because basically what we're doing is we're looking at two pairs of congruent angles. And if we can see those two pairs of congruent angles, then we can say that our two triangles must be similar. So in our diagram over here, we can see that angle A and angle D are marked congruent, and angle E and angle B are marked congruent. So since we have our two pairs of congruent angles, we can say that our two triangles are similar. And I forgot to mention on that last slide, this is the symbol right here for similar. It's kind of like the congruent symbol with the equals part taken off, right? Here's our congruent symbol. If we take off this equals part, we get this symbol, which is just like the tilde. That means similar to. And just like when we were doing triangles that were congruent and we had to be careful about the order in which we put these letters, we have to do the same thing in similar triangles. So when we say triangle ABC, we want to then list the other angles or the other corners of the second triangle in an order that shows what matches with what. So the fact that angle A and angle D are congruent means if A is listed first in this triangle's name, then the D will be listed first here. Since B and E are congruent, B listed second here means that E needs to be listed second here, and that would leave the third vertices to be listed as the third letter in our similarity statement. That's what we call that. We call that a similarity statement. Let me write that. That is called a similarity statement. And again, it kind of gives you some information about what parts match with what. So that's called angle-angle similarity, but that's only one of three shortcuts that we're going to have for triangles. So let's take a look at the other two real quick. Here we have our second one. This one's called side-side-side similarity, SSS similarity. Not to be confused with SSS congruence. This one's only proving that the triangles are similar, not congruent, which would mean exactly the same. So in side-side-side similarity, you can tell we need to know something about the lengths of all three sides of both triangles. And what we're going to be able to do is we're going to say, hey, if the corresponding sides of two triangles are proportional, then the triangles are similar. So what we want to be able to do in order to use side-side-side similarity is we want to match up pairs of sides that are corresponding to each other. So AB with DE, and we make a fraction out of those side lengths. And we do it with BC and EF. We think that those correspond to each other. And we do it with AC and DE because we think that those, or DF, I'm sorry, because we think that those correspond to each other. And so we make these fractions out of all of them. And to say that things are proportional means that these fractions will all equal each other, meaning that we can kind of reduce them down and have the same fraction each time. We might have different numbers in the fractions, but when we put those numbers in the fractions and we reduce the fractions, they all reduce to the same thing. And if I can do that with all three pairs of corresponding sides, then I can say that the triangles are similar by side, side, side similarity. And then the last similarity shortcut kind of combines those other two. This one's called side angle side similarity, or SAS similarity. So this one's like a combination of the last two, because what we're going to look at is we're going to look for one angle that's congruent to another angle. So one congruent angle pair. We can see here that angle B and angle E are congruent. And then the sides that include those angles. So that's a phrase that we've talked about before. Sides that include angles means that it's the sides that make the angle, the sides that we use to create that angle. So the sides that include angle B would be segment AB and segment CB. The sides that include angle E would be segment DE and segment FE. So those sides, the ones that include the two angles that are congruent, they have to be proportional. And if all that happens, we have our pair of congruent angles, we have our included side, our sides that include the angle, end up being proportional, then we can say that the triangles are similar. So again, we're looking at the angles here, and then AB matched up with DE in a fraction, and that will equal the other pair of sides in a fraction. AB over DE equals BC over EF. And if all that is true, then we can say that our triangles are similar by side, angle, side. So in this video, we looked at the definition of similarity, meaning that there's a similarity transformation that can be performed to move one shape onto the other. And a similarity transformation means that we are rotating, reflecting, and or translating the shape, and then also dilating it, making it smaller or bigger. Or we can think of it as two shapes are similar if all their corresponding angles are congruent and all their corresponding side lengths are proportional. But for triangles, we have these three shortcuts where we don't actually have to prove that all angles are congruent and all side lengths are proportional. We can kind of do certain combinations of those things, and that would be enough to prove that the triangles themselves are similar.